Question number 4 on page 420 is another situation where we are revolving a region around the x-axis. And this is the region that we have. The function is a semicircle. And if we rotate this over the x-axis, what we're going to get is a shape that looks kind of like a truncated cone. And I do know that if I slice this perpendicular to the axis about which I rotated, I'm going to get a series of very, very thin disks. And in fact, my disks will look like that. They're not going to be exact cylinders, but because they're thin enough, we can assume they are. And what I do know for a cylinder is that the volume is pi times the radius squared times the thickness. And the thickness of each of these is a little movement in the horizontal direction. So that's dx. What I know about each one is that the radius, no matter where I draw this, the radius is the distance from the x-axis all the way out to the curve. So the radius of this is nothing more than that big change in y. So from square root of 25 minus x squared all the way down to where y is equal to 0. So my radius is just square root of 25 minus x squared. I have infinitely many disks, and I'm just going to add them up. So I'm taking a Riemann sum of infinitely thin disks. So that's going to be pi times our radius squared, square root of 25 minus x squared times the thickness. And my limits of integration, x goes from 2 to 4. I'm even going to do this by hand because it's so easy. I'm going to pull out the pi. We're going from 2 to 4. This thing squared is just 25 minus x squared dx, which is going to give us pi 25x minus 1/3 x cubed between 2 and 4. And then you can plug in the limits of integration there. So that gives us 100 minus 64/3 for plugging in the 4. When we plug in the 2, we have 50 minus 8/3. And you can do the rest. But that's the heart and soul of that problem. And again, we're using the method of disks.